Very good morning, everybody. Welcome back to the class. So in today's chemistry class, it is going to be the last, as all of you know, for this particular session. I'll keep the last class today. And we were discussing about reaction mechanism and electron migration effects, where I've already discussed with you the electromeric effect as well as the inductive effect. Okay. Electromeric effect was not very much difficult. It was just two examples of addition reactions I gave. Plus E was there when electrophiles attacked on the alkene. There was a plus E electromeric effect, and minus E was when nucleophiles attacked on the aldehydes and ketones. These were the examples. Electromeric effect was a temporary effect because it worked only when the attacker is present. Inductive effect, on the other hand, was a permanent effect. Every time it will be there in all the organic compounds except for normal alkanes. Okay, in alkanes you will not see any inductive effect, but as soon as any functional group comes or unsaturation comes, then the sigma electrons start shifting from one end to another end, creating some inductive effect, creating some polarities. This was about inductive effect. It was permanent effect, as we have seen. It operates all the time. It is distance dependent, as we have seen, because when the distance was increasing, then the effect keeps on diminishing. It is only observed up to third atom of the carbon chain. After that it diminishes. I have shown you the examples here. It follows DNP, distance number power. In the applications we will see that. So acidic character, already I have told you in the application how to check the acidic character of carboxylic acids. Okay, when groups are present at same distance, you don't have to look at the distance, you don't have to look at the number, you have to look at the power. So the more powerful group makes the acidic character better if more powerful minus I is there. That is what we studied in the last class. So pullers make the acid strong and donors decrease the acidic strength. Pullers increase the acidic strength, donors decrease the acidic strength. For basic strength opposites, donor increase the basic strength, pullers decrease the basic strength. These are things we studied. Okay, these are the examples I have given. Please revise them again. If you have not watched the last video, you can watch the previous live video. Then we have seen some more examples of this. Okay, some more examples of basic character we have discussed here. After basic character, I discussed the stability of reaction intermediate based on inductive effect. Very few questions can be asked. So always when you check for the stability of any carbocation, always first check whether carbocation is undergoing any resonance or not. Okay, a resonance stabilized carbocation will always be much more stable than anything else. After you have checked for resonance, then you should check for hyperconjugation, which is number of alpha hydrogens. Check for number of alpha hydrogens, you will mostly get your answer here. In case you don't get the answer here as well, then check for inductive effect, which is at last we have to check. So inductive effect is a very, very weak effect as compared to M and H. So meso, the most important, then hyper, then inductive. Okay. So these are the things. Krishna, you can keep this down. Don't minimize. Okay. So, for example, these are the carbocations. A tertiary carbocation is better than secondary and primary because of more number of alpha hydrogen. Each alpha hydrogen will produce some hyperconjugative structure. Again, we checked in this case, again due to hyperconjugation we have seen. Again, we checked here. Here resonance was the deciding factor. More resonance, more stability. Less resonance, lesser stability. Among these two, this is tertiary, better than secondary. Then when you check for carbanion, directly check for resonance and then inductive. There is no hyperconjugation that you need to check because hyperconjugation will not exist here as you will study in your classes. Check for resonance, then check for inductive effect. So in this case, there is no resonance. I am directly checking for inductive effect. More plus I groups will destabilize the carbanion, and here no plus I group will make it very stable as we saw in the last class. This is due to resonance we have seen. Then I showed you more examples where this is again NO2 is showing resonance here, and this is the one. So this is our stability of some carbanions. Okay. Now we'll go to the next effect, which is going to be mesomeric effect and resonance. Mesomeric effect and resonance. First, we should know what is the meaning of resonance, and then we can talk about the mesomeric effect. Okay, so resonance means delocalization of some electrons. What is resonance? Delocalization of some electrons in a conjugated system. That is what resonance means. Okay, why do we need resonance, you might ask? We'll see that. Okay, resonance refers to delocalization. Delocalization means a pair of electrons will not be present at one single place, but it is possible to have a pair of electrons present at multiple different places. It is delocalized. It is not local only at one place, but it is delocal. It is present at many places. So it refers to delocalization of some pi electrons or some lone pair electrons. It refers to delocalization of some pi electrons or lone pair electrons in a conjugated system, in a conjugated planar system. This planar is also important. Okay, conjugated planar system. Planar means all the atoms where the conjugation is present must lie in the same plane. All the atoms on which conjugation is present must lie in the same plane. It is a necessary condition for resonance. It will mostly be true that whenever you see conjugation, planarity will be there, except for two particular cases, which will be in cyclooctatetraene and cyclodecapentaene. Okay, these two examples you can learn or remember them, that sometimes conjugation is present but planarity is not there. So there the resonance will not work. Otherwise, wherever there is conjugation, there will be planarity. Now, what is a conjugated system, beta? Conjugation. What is the meaning of conjugation or conjugated system? Conjugation just means alternate position pe there should be presence of pi electrons, like pi alternate to pi, or lone pair alternate to pi, and so on. So conjugation means presence of the following things: pi electrons, pi bond you can say, or you can say negative charge, or you can say lone pair, or you can say positive charge, or there can be even a free radical. Presence of pi bonds, negative charges, lone pair, positive charge, or a radical at alternate position to each other. At alternate position to each other. What do you mean alternate? Alternate means leaving one position. So you should be able to say like this: pi, nothing, pi. That becomes alternate. Pi, nothing, lone pair. That becomes alternate. Pi, nothing, plus. That becomes alternate. Plus, nothing, lone pair. That also becomes alternate. Okay, so you should be able to say like this. For example, I'll show you some conjugated system and some non-conjugated system. So conjugated system versus non-conjugated system. Okay, everybody, you can see here. When I have two pi bonds present like this, let's say, this is a non-conjugated system. There is no planarity here because this sp3 carbon comes in between, which loses its planarity. So there is no resonance possible here. So you can say in your words like pi, nothing, nothing, pi. So I'm not getting at alternate position. The pi bonds are not at alternate position. Whereas now they are at alternate position. You see, this is a conjugate system. Pi, nothing, pi. Okay. Let's take one more. Let's take pi, nothing, plus. You can look at this one. This is a conjugate system. So we can see that pi bond and the positive charge are alternate to each other. Pi, nothing, plus. From this side or this side you can see pi, nothing, plus. Pi, sigma, plus also you can say. Whereas a non-conjugated structure would be something like this. This is non-conjugated. Pi nothing nothing. Okay, I can see here pi nothing nothing. So plus is not in conjugation with the pi bond here. Something like this. Okay, let's see one more. If I look at, this is pyrrole beta, pyrrole. Pyrrole is a 5-membered ring with a nitrogen inside. So here you can see lone pair nothing pi nothing pi. This complete thing is a conjugated system. From here I am starting. Lone pair nothing pi nothing lone pair. There is a complete conjugation overall. But if I draw something like this, then there is no conjugation. Lone pair nothing, lone pair nothing nothing, lone pair sigma sigma, no conjugation is there. So in these cases conjugation is present, in those cases conjugation is not present. Another example, let me show you here. Everybody please see here. If I take example of this compound, let me take it like this. Versus I take the conjugate acid of this, NH3 positive. Okay. Some of you can do mistake here by saying, sir, here lone pair nothing pi. So this is conjugated. No doubt it is absolutely correct. Lone pair nothing pi, it is conjugated. Conjugation is possible. Whereas this is not conjugated, it looks conjugated. Pi nothing plus, it looks like this, pi nothing plus. But this is not conjugated beta. Okay, this is not conjugated. Why? Because if I try to send the pi electrons here by resonance, then nitrogen will have to make 5 bonds. And we know that nitrogen can never ever expand its octet. So this is not possible for this pi electron to get delocalized. It is impossible. So this is a non-conjugated system because this nitrogen is sp3. It is non-planar. It is sp3 nitrogen. It is non-planar and it cannot become sp2. It cannot become sp2. Although this nitrogen also looks sp3, but it can still delocalize its electron and get 4th bond and become sp2. So please remember beta. Please remember, whenever you see a NH3 positive or nitrogen with a positive charge, that positive charge can never undergo delocalization because otherwise nitrogen will have to make 5 bonds, which is impossible for nitrogen. But whenever nitrogen is neutral, its lone pair can be delocalized whenever you can find delocalization. Lone pair nothing pi, you can delocalize it, there is no problem. Lone pair nothing pi, you can delocalize it, no problem. But here this pi will not be delocalized on nitrogen because nitrogen will have to make 5th bond, which is not possible. Please remember this thing, okay? As an important example, you can learn this. Now we know what is the meaning of conjugation. Now let's see examples of conjugations and how the resonating structures are to be drawn. Some examples of drawing resonating structures. Resonating structures are also known as canonical forms. Canonical forms. Okay. Resonating structures are also known as canonical form. The first type of conjugation, let us take pi-pi conjugation. Pi-pi conjugation. I will take the simplest examples first. This is a pi-pi conjugation. Okay. So what do we do in the pi-pi conjugation is always you say like this, pi become pi, pi become minus. Okay. Pi become pi, pi become minus means, so these 4 carbons are under conjugation. They are planar carbon as all of you can see. This is sp2, 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 sp2. So resonance will only occur in these 4 carbons. Okay, nowhere else the resonance will go. So whenever there are 2 pi bonds alternate to each other, you can send from this side pi become pi, pi become minus. Like this you can see. Or the opposite side also you can send it your wish. Like this, make arrows. Whenever you draw 2 resonating structures, always represent by differentiating between them using a double-headed arrow like this. This arrow is used to define resonance, resonating structures. It is not equilibrium sign. Resonating structures are not real structures. You have studied in the chemical bonding chapter this already. Resonating structures are not real structures. These are imaginary structures. They don't exist actually. You can't isolate them. Okay, so this is one resonating form. If I move this electrons like this, then what will happen? See, this carbon has lost its electron, so it will become positively charged. This carbon gets double bond. This carbon has gained a pair of electron which gets a negative charge. This is one of the resonating structure, and the other resonating structure will be the opposite side. You can send it from here to here and you'll get the other resonating structure. If the movement of electron was in opposite side, then what will happen? If I said this pi moved ahead, so plus can come on this carbon and minus can come on this carbon. Okay, so this is called as the first type of conjugation, pi-pi conjugation, and this is how you draw the resonating structure. Pi become pi, pi become minus. Now when you take the average of all these resonating structures, you can see that pi bond could be present between these two carbon, or these two carbon. Everywhere pi bond can come. Pi bond can come here, pi bond can come here, pi bond can come here also. So that means I can show it like this. Two pi bonds are there which are distributed in these four carbons like this. This is the resonating structures. These are the resonating structures, and this average is the real structure. This is called as a resonance hybrid. This is only the real structure of this compound. Okay. Obviously, the pi bonds will not be equally distributed because these resonating structures do not equally contribute to the final average. Okay, it's not like this is 33%, this is 33%, this is 33%. No, not like that. Okay, the contribution from the resonating structures are not equal. They are according to their stability. You will see after some time that this is more stable as compared to these two structures. So like your resonance hybrid will 80% look like this, 20% only will look like this. Means these two carbons, this one and this one, here the pi bond density will be more as compared to between second and third carbon. Okay, that is not a concern. Nobody will ask you that, but I'm just telling you how to check the what all the resonance hybrid will consist of. It will be more like this and less like this. I'll tell you those rules as well. I hope first type of conjugation is clear to everybody. Pi-pi conjugation. Second one is beta. Second one is pi lone pair, or you can say pi negative conjugation. Both are similar to each other. Any one you can see. Pi lone pair conjugation or pi minus conjugation. Here don't start moving pi, always move lone pair. Okay, lone pair become pi, pi become minus. That is how you should say. LP become pi, pi become minus. Lone pair become pi, pi become minus, like this you should say. For example, I'll just give you one example. You can all see here. Okay. Let's take this example. Okay. So I'll just make it like this so that it's not a symmetrical molecule from both sides. So this is our negative charge. It is alternate to the pi bond. Minus nothing, pi is there. So never start moving the pi. Okay, because if you move the pi, pi become pi, then where will this minus go? There is no place to go, no? So always start by moving the minus. Minus also means lone pair. Carbon carrying a lone pair is a carbon ion. So lone pair is there. So always this lone pair will move. So you will say lone pair become pi, pi become minus. Now don't send this pi here beta, because conjugation cannot reach to this carbon. This carbon is a sp3 carbon. It is not planar. So conjugation, first you should think till where the conjugation can run. Till here only the conjugation runs. Lone pair, nothing pi. After this, no conjugation. Planarity has stopped after this. So you say, what do you say? You say lone pair become pi, pi become lone pair, or you say pi become minus. So minus become pi, pi become minus. So its other, canonical form is going to look like this. First draw all the sigma bonds and the atoms. Whenever you draw canonical forms, make sure that you never ever move any sigma bond. You never ever move any nuclei, means atom. Atoms' positions and sigma bonds position always remain fixed in resonating structures. Minus became pi, pi came here, and pi became minus, so minus came here. This is the resonating structure. And obviously you can draw its hybrid as well. Hybrid is going to look like this. Among first three carbons, the pi bond can oscillate here and here. And there is one negative charge, you have to show that. So that negative charge also oscillates here only. So I can show minus like this. This is the resonance hybrid of this particular compound. Okay, resonance hybrid is the real structure I have just told you. Let's take one more example. Now my question to you would be something like, in a plus pi conjugation, I can ask you something like, for this particular compound, this is called as troponium carbocation. For this particular carbocation, I can ask you that how many resonating structures are possible, or how many canonical forms are possible. Okay, how many canonical forms are possible? That could be my question to you. So how will you do it? There is no, first of all, formula. Okay, there is no formula to find this out. You have to draw the canonical form and check. So you will see that once you draw, this positive charge could go on any of the 7 carbons. It could go on any of the 7 carbons. So you can get total 7 canonical structures. I'll show you how to draw. Okay. So what to do when there is a pi nothing plus conjugation? Plus means there is no electron pair. No, plus means electron deficient. So here up to now you are getting two arrows. No, pi become pi, pi become minus, lone pair become pi, pi become lone pair. Now you will get a single arrow here. Just you say pi become pi. Just you say pi become pi. So make any pi bond move ahead. Pi nothing plus, pi become pi. So pi came here. Once the pi bond comes here, the next structure is looking like this. So see here, pi came here. So this carbon has lost its electron. So this carbon will become positively charged. Rest everything as it is. Correct? Again, you can move it ahead. Pi nothing plus, pi become pi. Okay. So pi has come here. This carbon has lost its electron. So this becomes positively charged. Rest everything as it is. Then this pi can move ahead. Pi become pi. Okay. From inside I am showing. It's a 7-membered ring. So make sure you are making 7. Now this carbon has lost its electron. This becomes positive like this. So you can see that positive charge will keep coming everywhere. Now pi becomes pi. This pi can be moved ahead. This carbon will get the positive charge. Here. Something like this. Okay. And then again, pi becomes pi. Now this carbon will get the positive charge. Rest everything as it is. So you can see I have made how many? 1, 2, 3, 4, 5, 6 and one more. Pi become pi. Now this carbon gets the positive charge. And then finally, when you say pi become pi, positive charge goes back and the first structure comes out. So you'll get back to your first structure. So total 7 different structures are there. So here example, we have written answer as 7 resonating structures. Okay, like this you can say. There are 7 resonating structures which we have made for a troponium cation. I hope it is clear to everybody. Same way, this is also a very stable carbocation. It will have 3 structures because plus can go to 3 carbons. So 3 structures will be present here. Okay, so this is the one. Then there can be a radical conjugation as well, where radical can only conjugate with a pi bond. And the last type of conjugation is radical pi conjugation. Radical pi conjugation. I'll show you with a good example. Let's take a benzyl free radical, this one. Benzyl free radical. Whenever there is a radical, how the conjugation will run? You say radical become pi, pi become radical. Radical become pi, pi become radical. And you know that whenever you move a single electron, you always show a fish head arrow, not a complete arrow. So I will say that radical you become pi, you come here. Radical says only one electron, how will I make a pi bond? So we'll say, okay, this pi bond also will split homolytically, one coming to you, one going to the next carbon. So what I'm doing here, radical with this radical became a pi bond, and here a radical is generated. So you can say radical became pi, pi became radical. This radical became pi. This radical became pi. This pi bond became a radical. Like this. At ortho position it has come. Now let's move it ahead. Radical become pi, you become radical. Keeping that 6-membered ring as it is. Here we get a radical. Here we get the new pi bond. Here was the old pi bond. Again I can say radical you become pi, pi you become radical. So the next structure is going to look like this. This CH2 as it is. Here we get the new radical and here we get the new pi bond. This is the old pi bond. And the next time it will go back and you will get your similar looking to first structure, not same as first structure. You see beta, in the benzene ring, the bonds would have shifted. So this is a new structure. Radical become pi, pi become radical. So first and the last structure are not same, but they are similar. They are not same, but they are similar. You can see that the position of the pi bonds in the benzene ring has reversed. Initially, the pi bonds were on this side, now they are on the opposite side. You can just see that they are not same, but they are different. Okay, so this is how we can talk about radical to pi conjugation, and we can draw the conjugating structures. Okay, I hope this is clear to everybody. You can write it down. I'll give you a little bit time, then we'll move on to the next one. So other type of conjugations, some of them are not possible. So what are the not possible conjugation? Not possible conjugations are plus plus conjugation. Obviously, how 2 plus will be conjugated? This is not possible because there are no electrons to move. Something like CH2 positive, CH2 positive, there is not a conjugation. So although there is a plus nothing plus, but such a conjugation is not possible. Plus nothing radical, there is no conjugation like that. Okay, plus nothing radical, there is no conjugation like that. Radical radical, there is no such conjugation. Okay, so these are not possible ones. Minus with plus can be there. Minus with plus or lone pair with plus. So minus plus conjugation or lone pair plus conjugation is possible. It is very, very stabilizing conjugation. Whenever minus and plus or lone pair and plus come next to each other, something like CH2 positive with the NH2 group. This is a very, very good conjugation. We also call it as back bonding. So here this lone pair nothing plus, lone pair nothing plus, they are in conjugation. So lone pair become pi. So it will give you CH2 double bond NH2. Whenever nitrogen makes fourth bond, it gets a positive charge. So positive charges come from here to here. So this type of conjugation is possible. Okay, this type of conjugation is possible. We call it as back bonding also. Okay, you can call it as back bonding as well. Okay, because this pi bond is just created by back donation to the electron deficient atom, which is carbon. So it is called as back bonding as well. Okay, so these are the ones that we can think of right now. So I hope you can write the resonating structures yourself now. Now, next point comes, how do we check the contribution of resonating structures in the hybrid? So you'll write down factors affecting stability slash contribution of canonical forms. So whichever canonical form will be more stable, that will contribute more. That will contribute more to the resonance hybrid. Okay, the one which is more stable will contribute more to the resonance hybrid. So you can first write down this point as a note point. Percentage contribution to the hybrid, resonance hybrid, is directly proportional to the stability of canonical form. Stability of canonical form. Now, how do you check the stability? Always check it step by step, beta. Always check it step by step. Okay, what is step number one? Step number one is the first most important point. More the number of bonds, more the stability or contribution. So first thing is contribution is directly proportional to, contribution or stability is directly proportional to total number of bonds in canonical form. So more bonds, more contribution. More bonds, more contribution. One example, let me show. If I draw butadiene and I show its resonating structure, its other resonating structure will look like this. Pi become big, pi become minus, negative comes here, positive comes here, and pi bond comes here. So among these two, A is more stable than B. So A will contribute more as compared to B. So contribution order will be A more than B. Okay. So as soon as the molecule comes to you, the very first thing you will do is you will check the number of bonds. What you could also check is, along with this only you check, contribution is directly proportional to complete octets. More the number of complete octets, more will be the contribution. So this is the next one. Contribution is directly proportional to complete octets. That means octet rule we have to check. Because in the organic compound, mostly your central atom will be a carbon or oxygen or nitrogen. They should follow octet rule to become stable. So whenever you can check in the first one also here, beta, this carbon has incomplete octet. A carbocation has 6 electrons. So in this case, it's an incomplete octet. That's why it is unstable. Okay. In some other cases, when bonds are equal, sometimes you might have to check the complete octets. For example, let me show you this particular one. Okay. Let me take this particular example. Okay, where the octet will be used, mostly it will be in the case of, okay, I'll show you this example. You can see it from here. See, the number of complete octets and the number of bonds in the canonical form, these two things will always overlap with each other. 90% of the time, they will overlap. So by checking the bonds only, you can decide everything. For example, if I take CH3 C double bond O and a positive charge here. This is an acyl carbocation. Okay, it is a acyl carbocation. In this carbon has an incomplete octet. Now, if I draw its resonating structure, you can see here this lone pair and this positive charge are alternate to each other. So I can say lone pair become pi, and its next resonating structure is going to look like this: CH3 C triple bond O, and O will get a positive charge because O has lost its electron. Okay, so among these two, again, B is more stable than A, because in B, this carbon has complete octet. This oxygen also has complete octet. Do not worry about it. You can see here, this oxygen had 2 plus 2 plus 2 plus 2, 8 electron. Now also it has 3 sigma bonds and 1 lone pair. Still it is 8 electrons only. So in this case, this is incomplete octet. In this case, it is complete octet. Even if you don't know this rule, you could directly check it from the number of bonds. More the bonds, more the stability. So here between A and B, B is more stable than A. B contributes more than A. Okay. So when you know the concept of number of bonds, even if you forget about the octet rule, okay, you can still get the answer correctly. So this is the one. After you have checked for this, next point you can say, third point, which is a neutral canonical form is more stable than the charged canonical form. So you can say third point, contribution of neutral canonical form is more than contribution of charged canonical form. Okay. Sometimes bonds may remain same. But the charge will start coming in the canonical form. That time you say neutral canonical form is better than the charged canonical form. For example, I will show you this particular example. Okay, if I look at this particular example. Yes, Kareem. So lone pair and pi are in conjugation. I can say lone pair become pi, pi become minus. So when lone pair become pi, pi bond comes here, pi goes there, become minus. Because nitrogen has lost its lone pair of electrons, so nitrogen, whenever it makes 4 bonds, it always gets a positive charge, you already know. So it will get a plus minus. So you can see here that in this case there is some charge separation. So plus minus is visible. Overall charge on every resonating structure anyways will remain same. Okay, so if first person is neutral, second will also be overall neutral. But still there is some charge separation present here. So this is not so good. First one is good. So here A is better than B. A is better than B. Okay. So after you've checked for the bonds, so you can see here bonds are equal. Here also there is one pi bond. Here also there is one pi bond. So when bonds are equal, you could go and check for the I told you, you can go and check for the charges. Okay. Then go to number 4. At number 4, now you check the distance between the charges. Okay. Whenever there are opposite charges are found to be stable when they are near to each other. Okay. Plus minus near are good because they will attract each other. And if there are same charges plus plus, then far away they are better. So plus plus must be far away, plus minus must be near to each other. So next thing is contribution is inversely proportional to distance between opposite charges. Distance between plus and minus, and directly proportional to distance between plus and plus or minus and minus. So similar charges away are better, opposite charges near are better. Okay, you can see the example here. For example, if I give you, okay, this is one canonical form number 1. Second canonical form I'm drawing like this. Okay, second one I'm drawing like this, and third one I am drawing like this. Okay, something like this. So what I have done here is I have sent this pi bond ahead, pi become minus, so I get a plus here and a minus here. Then I've just made one more canonical form by sending this minus even forward. Minus become pi become minus. I have made this one. Okay. So you can all see here that among these, first thing I'll check the number of bonds. A has more bonds than B. B and C have equal number of bonds. In A, there are 3 pi bonds. In B, there are 2 pi bonds. In C, there are 2 pi bonds. So between B and C, pi bonds are equal. I'll check for the octet. Here also one incomplete octet. There also one incomplete octet is there. So octets are also same. Octets are same. Bonds are same. Then what do we check? Charge. Both are charged. Next thing, we check the distance of the charge. Charges are opposite. Near are better. So this is better than this one. So A is the best. More bonds. Then B is good. C is the worst because plus minus have gone very much far away from each other. So A, B, C is the order. Like this you can say. A, B, C is the order. Okay, if charges are plus plus, then what do we do? You can see here. If charges are plus plus, then what do? We do opposite. Example next, you can see here. What I am doing here is I am putting a NO2 here. NO2 can be written like this. Okay, NO2 means there is an N coordinate bond O. You can also write it like this, N plus O minus. Now let's say there is a pi and pi alternate to each other here, like this. Now you can see here that conjugation is between these two pi's. So I can send them either this side or that side. So if I send them to NO2 side, let's say. If I send them to NO2 side, I will say pi become pi, pi become minus. Pi become pi, pi become minus. So plus comes here, pi comes here, and minus comes here. Okay. And the next one, if I send it the opposite side, if I send it the opposite side, then I'll say plus become pi become pi, pi become minus, then positive charge will come here. Minus will go there. Okay. So here you can see that the plus and plus are far away from each other. This plus and this plus are far away from each other. That is good. That is good. Here the two plus have come close to each other. They will repel each other, making it very, very unstable. So plus plus should be far away, plus minus should be near. This is the best because it has more number of bonds. So out of the A, B, C again is the order. A is better than B is better than C. Okay. Like this we can decide the stability in this case. Now comes the last one, the fifth point, which is the last point. In case distance is also same, whenever all these things are same, bonds are same, octets are same, charges are same, distance between the charges are also same, then only then the last thing that you will check is going to be the symmetry of the charge separation. Symmetrical charge separation is better than asymmetrical charge separation. So symmetrical charge separation. Always check it at last. Okay, don't check it the very first thing, otherwise you'll do mistake. If you start checking this as the very first thing, then you will do mistake. So symmetrical charge separation is more contributing than asymmetrical charge separation. Then you might say, sir, what is symmetrical, what is asymmetrical? Symmetrical charge separation means, according to law of nature, means if God has created oxygen more electronegative and carbon more electropositive, then oxygen pe negative charge is more stable because oxygen is more electronegative and carbon pe positive charge is more stable. That is symmetrical charge separation, that electropositive person gets plus, electronegative person gets minus. That is symmetrical. If you do opposite, oxygen getting plus and carbon getting minus, it is not good. So you can just mention this point. Symmetrical charge separation is better than asymmetrical charge separation. Symmetrical means, this means electronegative gets negative charge, electropositive gets positive charge. And here opposite, asymmetrical means electronegative gets positive charge and electropositive gets negative charge. This is not good. This is good. But only check it at last. Don't check it in between. Okay. So let me show you one example from here as well. For example, if I take this conjugated aldehyde, I can draw canonical forms in two ways. You can see that there is a pi-pi conjugation. One way is to send the electron towards the oxygen. Pi become pi, pi become minus. This is one way. So you will get CH2, single bond CH, single bond C, O, H. What has happened? Pi became pi. So this pi came here, giving a positive charge to this carbon. This pi went to oxygen, giving a negative charge to oxygen. This is first canonical form. Other canonical form I can make it if I send the pi electrons in the opposite direction. If I send the pi electrons in the opposite direction, which will go like this. Pi become pi, pi become minus. This is also possible. If I do like that, then I am going to reach here. CH2, CH, CH, O. Pi becomes pi, so pi comes here. Pi becomes minus, so minus goes here. This is the second one. Okay. This is the second one. Now in this case, bonds wise A is the best. Neutral wise also A is the best. A is the best. Between B and C, if I want to check, charge separation is there, bonds are equal, octets are also same only because here this octet is incomplete beta. Here this octet is incomplete, O positive. Okay, here oxygen had, 2 lone pairs. It has 3 lone pairs now. It still has 2 lone pairs. So this is incomplete octet. So 1 octet is incomplete. Okay. Then we go to next, charge separation ka distance. Distance is same beta. Here also distance is 1 and 4. Here also distance is 1 and 4. And last thing we go for symmetrical, asymmetrical. In this case, carbon is getting a plus charge and oxygen is getting a minus charge, which is a very good thing because carbon is electropositive as compared to oxygen. It should get a positive charge. Here oxygen is getting a positive charge, which is not at all according to the nature of oxygen. So it will be unhappy. So again answer will be A better than B better than C. Okay, but same thing, you should not check it in this example. If you look at this example, everybody, let's say this is one example that I am sharing with you. First one and second one. Okay, this is first example, this is second example. So two canonical forms I have given here. If I ask you which is more stable, don't say, sir, carbon is having plus charge here, oxygen is having plus charge. Don't do like that. Other rules are there, no? Start from rule 1. More bonds, more stable. So although oxygen is getting a positive charge, but still this resonating structure is more stable. Why? Because our first criteria was to check the number of bonds or to check the number of complete octets. You can see here, everybody. In this case, this carbon had an incomplete octet. This carbon is unhappy because it has a incomplete octet. Now you see everyone has a complete octet. Here oxygen also has a complete octet only. So when O has a one bond and positive charge, it is incomplete octet. But when oxygen has 3 bonds and a positive charge, there is no problem. There is a complete octet. This carbon is also complete octet. All carbons, all oxygens, everything is complete octet. That is why A is much better than B here. So don't directly check for symmetry of the charges. Okay, symmetry of the charges, do not check directly. First come from the very first point, which is going to be starting with the number of bonds, then with the octets, then other things. And this is the last thing you need to check, which is the symmetry of the charges. I hope it is clear to everybody. I'll give you 2 minutes to write it down. Then we'll continue further with what is mesomeric effect. Why not? Yes, yes, B better than A better, not A better than B. I just told you. More the bonds, more the stability. B better than A, not A better than B. Okay. B is better than A. So this is about our, rules to check the stability of canonical form and who will contribute more in the resonance hybrid. So direct questions can come from these rules, as I showed you some questions, same way they can be asked. Now we'll talk about what is a mesomeric effect, or we can call it as M effect. We can call it as a M effect. Just like there is a plus I minus I, there is plus M minus M. Okay, there is plus M minus M. What is a plus M group? Whenever some groups donate the electron through resonance, they become plus M group. So first we'll start with plus M effect. Please remember it, beta. Whenever you see mesomeric effect, generally you will see it on the benzene ring on a conjugated system. There can be open conjugated system also, but 90% of the time questions will come from the benzene ring. So whenever you attach a group to the benzene ring, and a group is such that it carries a lone pair, the directly attached atom to the benzene ring carries a lone pair. These groups are called as plus M groups. These groups are called as plus M groups. Function groups like OH, O will carry lone pair, OR, okay, alkoxide, alcohol. Then you can have NH2. These are all plus M groups, okay. These are all plus M groups. So this is how you can easily remember which are the plus M groups. Groups which carry lone pair on the atom directly attached to benzene ring. So we can mention plus M effect. Groups like OH, OR, NHCOR, NH2, halogen like fluorine, chlorine, bromine. Okay, they are also plus M. Is NH2, NHR, secondary amine, NR2, tertiary amine. These donate their lone pair of electrons to the conjugated system, are plus M groups and are called as plus M group. So it a very important thing. These particular groups, all of these that I've mentioned here, they are actually minus I as well. So when they are not attached to conjugation, they are pullers. OH is a puller, NH2 is a puller, OR is a puller. These are all more electronegative than carbon. So they are puller by the inductive effect. But when they attach to benzene, they become givers. So they are called as plus M groups. So they are plus M as well as minus I. They are plus M as well as minus I. Okay. So they are electron withdrawing tendency by inductive effect, but they have electron donating tendency when it comes to mesomeric effect. Because mesomeric effect is more stronger effect than inductive effect, so they are generally considered as donor whenever they are attached to conjugation. Whenever they are attached to conjugation, you consider them as donors, not the pullers. When they are not attached to conjugation, then they are pullers. For example, I have shown you a few examples in the inductive effect. I never showed you any conjugation there. In the inductive effect, when I took the examples, you can see here. In the inductive effect, when I took the examples, like here, look at fluorine. This fluorine is actually plus M group, but here I am just taking it as minus I because the lone pair of fluorine is not in any conjugation. Okay, here chlorine also not in any conjugation, so I have taken it as minus I. So same way, whenever you see conjugation, you will take them as plus M or the donors. When you don't see conjugation, you can directly go for inductive effect and say them as minus I group. So what they will do? So see here, effect of plus M on benzene ring. Effect of any plus M group on benzene ring. Beta, on a benzene ring, a plus M shows two effects. First thing, it donates electron where? Only at its ortho and para position. Only at its ortho and para position, nowhere else. Okay, only at its ortho and para position. So plus M, when you put it on benzene ring, you can see here, if I take a plus M group like OH, so I'm taking phenol. Let us draw all the resonating structures of phenol and see what happens. So I told you always lone pair start moving, lone pair become pi, pi become minus. So the first resonating structure is coming out something like this. I'll just draw all of them. Okay, see here better. So lone pair become pi, this became double bond, pi became minus, so this pi bond became negative charge here. This is the first structure. So lone pair has sent its electron to only ortho position till now. Then pi become minus become pi, pi become minus. This minus become pi here, this pi become minus here. So we get pi bond here and a minus charge here. Then minus becomes pi, pi becomes minus again once again. So we get to, also there was a double bond here, and oxygen gets a positive charge because it has donated its electron. So oxygen gets a plus charge now. So again, positive charge here. This is pi bond. This minus became pi here and I get a minus here. Again we say minus become pi, pi become minus. Minus become pi, pi become minus. So we get back our similar to the first structure, but all the bonds are rotated now. Like this, like this, like this. So these are the 5 resonating structures that I've drawn for the phenol. Now what you can see here clearly is that where did the electrons go? You can see here beta, electrons have gone to ortho position. Electron has gone to ortho position, para position and back to ortho position. Electron has never gone to the meta position. Here and here electron has never gone. That means our plus M groups are ortho para directing in nature. So the influence of plus M is first one, they are ortho para directing in nature. All of you must be knowing the meaning of ortho para direction is that whenever any electrophile will come to attack on them, whenever you do nitration reaction of phenol, nitration of phenol if you do, nitro group, NO2 positive group, the electrophile will ask where should I go and attach. OH will say I have sent electrons to ortho and para position, please go and attach there. So that's why you get picric acid as the product, where ortho and para nitro phenol you will get. So they are called as ortho para directing groups because they direct means to tell. They direct electrophile to their ortho and para position, and they are also called as ring activating groups. They are ring activating groups except halogens, as Kareem has clearly mentioned in the chat box, except halogens. Beta, for halogens it is found that their minus I effect is more dominant over their plus M effect. So overall they are pulling in nature as compared to donating. But all the other functional groups, which is OH, NH2, NHR, for them Plus M is much stronger than minus I. So they send electron to the benzene ring, making the benzene ring electron rich. And whenever benzene ring is electron rich, it easily can attack on the electrophile, and we call it as an activated ring. We call it as a activated ring. So they help in the activation of benzene ring. So they are also called as ring activating groups. Okay. So two things about plus M I have told you. Same way, two things about minus M now. The final topic for the today is minus M effect or minus M groups. Easy to remember, beta, whenever benzene ring is attached to any group which is of the type A double bond B or A triple bond B, where the directly attached atom does not have a lone pair but it has a pi bond. It has a pi bond. In that case, and B should be more electronegative than A. B is more electronegative than A. Such functional groups like aldehydes, where C double bond O will be there, ketones like carboxylic acids, like nitro group, like cyano group, like sulfonic acid group. Okay, all these groups, they act as minus I, minus M. Minus M also, minus I also. Obviously, they are all minus I as well. So these groups withdraw electrons from conjugated system. And called as minus M groups. Are called as minus M groups. For example, let's see how they influence benzene ring. How do they influence when they attach to benzene ring? Let's say this is benzene ring, beta. I am making a benzaldehyde. I am attaching C double bond O H here. This is benzaldehyde. We know oxygen is more electronegative than carbon. So oxygen is a good puller. Oxygen will say, send the conjugation towards me. Pi become pi, pi become minus. Pi become pi, pi become minus. So this is what we'll do. Pi become pi, pi become minus. So we get a negative charge here and a positive charge here. Now there is a conjugation between plus and pi. So we can say pi moves ahead. So we get a positive charge here. Now this pi and this plus can show conjugation. Pi becomes pi. We get a plus charge here. Then this plus and this pi. So minus become pi, pi become pi. We'll go back to the original structure and it will start looking like this, with all the bonds rotated. These are the 5 resonating structures of benzaldehyde. So phenol also has 5 resonating structures. Benzaldehyde also has 5 resonating structures. Here you can see positive charge is created on the benzene ring, means benzene is becoming electron deficient. So they are ring deactivating in nature. Minus M groups are ring deactivating in nature. And they are actually called as meta-directing groups. It does not mean that they pull electrons from meta position, beta. They are pulling electron from ortho and para position. So when an electrophile will come, when an NO2 plus will come and say, where should I go and attach? So benzaldehyde will say, please go and attach to meta position because I have not pulled any electrons from there. I have pulled electrons from ortho para. So don't go to ortho para. Those are deactivated positions. So only position left is meta. you can go and sit there. So that is the only thing that we want to talk about. So this is all about our today's lecture. I hope you have enjoyed these bridge classes. Thank you and bye bye.